Question 6, and this is the last question of this particular pack on structure and bonding, states whether the following substances conduct electricity when solid or molten, and explain your answer in terms of the particles involved. So once again, you're being asked to mention the particles present. All right, it's another rehash of the same basic question. We're being asked to explain a different concept this time, but the idea of the attractions and the particles is there once more. So state whether the following substances conduct electricity when solid or molten. Let's just stop there for a second, go through the options we've got, and say whether we know for a fact whether they'll conduct electricity or not. So we've got aluminium. Aluminium is metallic. Okay, so a metal will conduct electricity when it's solid and when it's molten. All right, it doesn't matter if you melt it or not, it will still have the same particles, that everything becomes mobile, it will still be able to conduct electricity. So this is conductive when solid and molten. Aluminium fluoride, metal, non-metal, this is an ionic substance. Okay, so we can anticipate then, and any ionic substance will conduct when molten, not when solid. We'll explain why in a brief time. Boron tribromide. Okay, boron, bromine, both covalent. This is a simple covalent molecule. You're not going to get a tribromide. So for every boron, there's 3 bromines attached. Boron can only make three covalent bonds. So here we have a simple covalent molecule. Okay, so the first trick with this one is to make sure you recognize what type of structure you've got in all 3 of your chemicals. So metallic, giant ionic, simple covalent. So this is non-conductive. Okay, simple covalent lattices do not conduct electricity. So let's explain these observations then in terms of the particles involved. So we'll start with aluminium. Okay, we've already stated it's metallic there in my explanations, but let's construct a proper answer in the answer line. So aluminium, we have a giant metallic lattice. Let's state the structure, just to be careful. Okay, so we have, because it's metallic, it can conduct electricity when solid and molten. I'm going to put it in capitals because it's that bit you tend to forget. Solid and molten, because why does a metal attract electricity? It has delocalized electrons. Can move. Okay, so metals, whether they're solid or molten, will always have delocalized electrons. Okay, in solid, obviously the ions are fixed in the lattice structure, but the electrons are delocalized. When you melt it down, all the ions and the electrons are mobile. We still only use the term delocalized when we're referring to electrons. We wouldn't say delocalized ions. It's a bit of a misnomer, because the ions aren't delocalized. They can move when you melt the substance down. We don't refer to them as delocalized. Only electrons can be delocalized. So that's our aluminium. We've got aluminium fluoride, which will be AlF3. Obviously, it's not asking for its chemical formula, but I'm just shorthanding it here. All right, to explain that, aluminium's a +3 charge, 3 electrons is lost. Fluorine, group 7, gains 1 electron, so I'd need 3 fluorines to cancel out the aluminium. So there's the chemical formula for aluminium fluoride. We know it's ionic, so let's put the structure in there. A giant ionic lattice. Okay, so we can say it conducts when molten, because the ions are mobile. So remember, with the ionic lattices, it's not electrons. Okay, electrons are only involved in conductivity in metals and in your layered covalent substances like graphite and graphene. Okay, when it comes to ionic substances, it's the ions that are going to be able to conduct the charge, and that only happens when the lattice is molten or when you've dissolved it in solution. That allows the ions to become mobile. So you have to make reference to that, and again, do not say delocalized. And don't say free either. Same up here, you cannot say free. Delocalized electrons, ions that are mobile. Okay, giant ionic lattice conducts when molten because the ions are mobile, and does not conduct when solid because the ions are fixed in the lattice. Okay, make it nice and clear where they are. Okay, rather than just saying simply the ions are fixed or ions are not mobile. Why are they not mobile? Because they're fixed in the lattice. And lastly, boron tribromide, BBr3. This is a simple covalent molecule, a simple covalent lattice. This is non-conductive. Why? Because there are no, once again using the word mobile, charged particles. Okay, so the charged particles is a collective term for ions and electrons. So you can't use the term charged particles up here for your ionic lattice because we want to specify that it's ions that are going to be able to move to conduct the charge when you melt the lattice down. With simple covalent molecules and simple covalent lattices, there's no ions, there's no delocalized electrons, and both of those are your charged particles. So we can use this branch term, or collective term, of no mobile charged particles. 5 marks for that question then. It'll be breaking that down then. 1 mark for aluminium conducting when solid and molten, so there's 1 there. 2nd mark for delocalized electrons. 3rd mark is going to be aluminium fluoride conducts when molten, and because the ions are mobile. So this whole statement here is marked number 3. This whole statement here will be marked number 4. It does not conduct when solid because the ions are fixed in the lattice. Mark number 5 is the BBr3 has been non-conductive because there are no mobile charged particles. Okay. Answer as fully as you can, but try and keep it concise. Examiners don't like waffle, and I'm pretty sure your teachers will not like waffle either. I know I certainly don't. So make sure you focus on the key points in your answer and keep it concise.